Good day, and welcome to CFE Media's Virtual Training Week. For this session on motor management and troubleshooting techniques for AC induction motors, we'll be joined by Michael Lida, Laboratory Director of the Motor Lab at Raleigh, North Carolina-based Advanced Energy Corporation. I'm Kevin Parker, an editor with CFE Media. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be issued to each participant. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. Over their operating lives, most AC induction motors exhibit common problems, from transients to voltage imbalances and single phasing. Therefore, being familiar with general troubleshooting techniques is important. To start, it's vital to understand the operating parameters and forces acting against the motor, to perform tests and make observations based on those parameters, and to remove system components to isolate a problem. Proper size and power source connection must be verified. Regular measurement procedures, starting with nominal voltage, current, and frequency, can be the starting point for long-running optimal motor and drive operation. This webcast will specify and analyze the various troubleshooting operating parameters to consider and outline what equipment is needed to identify solutions. You see before you the learning objectives for today's session. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you would like to take notes within the session, click on the left panel labeled Notes to do so. Please remember that this session will be made live at 10 a.m. Central, 11 a.m. Eastern. Want to take the session again? No problem. This session will be available on demand. If you're experiencing difficulties, please log out and back into the session to continue. Attendees are eligible for 1 PDH credit for this event airing on October 17th, 2022, and is categorized within the Technical Health and Safety, including Core Technology category for RECEP. This event is a live educational session presented on October 17th, 2022, and on demand afterward. I'd now like to introduce today's speaker. Michael Lida started working for the Advanced Energy Motor Lab in January 2010 as a co-op student. After completing an engineering fellowship with Advanced Energy, Michael moved into the Motor Lab coordinator role in 2013. With extensive testing experience in the lab, Michael became lab director in 2019. Today's Michael's efforts are devoted to motor system testing development, research, and training on a wide range of applications. Michael is also a member of the Advanced Energy Commercial and Industrial team, participating in energy assessments and recommending energy conservation measures at regional facilities. Michael received his bachelor's degree in electrical and computer engineering and a minor in mathematics from North Carolina State University. Michael, welcome to today's virtual training session, and please go ahead.
Thanks, Kevin. Really appreciate the introduction and appreciate you having me back for another session here with Virtual Training Week. Enjoyed participating last year. I think it was a great success for our industry, and happy to be back. I would like to start with a brief background on Advanced Energy, and then we'll move into the motors and maintenance material. Advanced Energy was founded back in 1980 by the Public Utilities Commission here in the state of North Carolina, founded to investigate and implement new technologies for load management, conservation, energy efficiency, distributed generation, and other things. We are an independent nonprofit corporation. We have a board of directors that's appointed by the governor of the state of North Carolina and our member utilities. We did just celebrate and had a nice, impact report that we released a couple years ago on our 40-year anniversary. We continue to work with our member utilities, Duke Energy, Dominion, North Carolina Power, and the North Carolina Electric Membership Corporation on energy efficiency and conservation projects now. In addition to creating means for sustainable energy efficient economic development for the ratepayers of our state, we do operate as a fee-for-service consultant to clients nationally as well as internationally. We work with other electric utilities, governments, and wide varieties of organizations in our 5 main areas, which are residential, C&I, commercial and industrial, renewables, primarily solar, motors and drives, and then also electric vehicles. And our customized services include research, testing, training, consulting, and program design. So now a little specific on the lab itself. I am on the large business and industry team. So that comprises our commercial and industrial group and our motors and drives group. My primary responsibilities, as Kevin alluded to, are focused around motors and drives testing, mainly motor testing, and then also getting out into industrial facilities and performing energy assessments. If you would like to find out more information about Advanced Energy, feel free to go to our website. There are multiple Advanced Energies, so we are the .org version. So our website is www.advancedenergy.org. Now let's get to it. So we'll move in to the material. So what we've done is broken the content today down into 4 categories. So, motor management, we're going to cover kind of at the end. And then the first 3 areas will be the troubleshooting techniques. We're going to start with some of the forces acting against a motor when it's in operation. Then we'll review some test equipment and test methods to use when you're doing your troubleshooting, and then diagnose symptoms and solve those problems with whatever that test equipment may be. And again, we're going to finish up with kind of motor management. The motor management will be last. Don't let it be kind of degraded. It's very important for overall energy efficiency and kind of energy savings of your plant, as well as downtime, reducing downtime. So first here, we're going to start with some forces acting against the motor. I think, we have covered some of this content in previous presentations, but we want to review some of the basics here first before we get into anything else. So during operation, you have, certain forces acting against the motor. We've listed on the screen. For a motor to perform within its design specs, what's on its nameplate or what comes from the manufacturer literature, you want to keep that running temperature, at or below the installation class rating. We'll go a little bit deeper on installation class rating in a few slides. The voltage you've got on the input of the motor leads should also be well balanced and close to that nameplate rating as possible. And the balanced really comes in for 3-phase motors. Single phase motors, you just have the 1 voltage, but we're going to be focused primarily on, industrial size machines today, AC induction, industrial size machines, or maybe some smaller commercial or larger commercial applications. So incoming voltage coming from your utility or input distribution transformer definitely needs to be kept at as balanced as possible. And then the third force we'll look at is the mechanical friction. So, how do you overcome the mechanical friction during startup? So here we have a nice graphic. We're looking at kind of where does the temperature come from, as the motor is running. Where does, not temperature, but where does the heat come from that's increasing the temperature inside the machine? Because one thing to take out of the presentation is heat is typically going to be your primary source of damage to motor components. So excessive heat occurs from a lot of different things. A few examples would be elevated ambient temperature. If you're in the you got motors in the deep in the earth, or in a high temp environment, elevated ambience. We already discussed a little bit the unbalanced voltage on the mains terminals. Or if you've got like a fan cooled motor, if the fan is blocked or has some kind of limited cooling, that's going to cause increased heat. It's not getting the air movement that it needs to stay cool across the cooling fins. If the motor is under overload condition, so under a load higher than its nameplate rating, typically that's going to add heat. And then also vibration if you have shaft misalignment, or if the wrong motor is matched to the application, that could lead to vibration. Vibration leads to heat, typically in the motor bearings. Oops. And then the next section here, I said a few minutes ago, we would discuss insulation class. So when we talk about heat, and motor temperature, so what is insulation class and what is the appropriate operating temperature for a specific motor? And that's where NEMA, the National Electric Manufacturers Association, and IEC in Europe, International Electrotechnical Commission, they've standardized the operating temperature reporting, and that's termed insulation class. So motors in general will be rated with the insulation class, and that applies to the insulation on the motor windings, really generally very tiny wires, those electrical wires inside the motor. But the bearings and other components inside the motor also are going to be rated, for some type of temp rating. The insulation class will typically be the lowest temperature compared to all the other components. So kind of the maximum you want to run that motor at is going to be that insulation class temp. If you look at the NEMA rating specifically, what we've shown here on the bottom left of the screen, the higher the letter, the hotter the motor could get in theory. So, if you look at class H on the far right, that's rated to run at a higher temperature than class F insulation. So definitely pay attention to the motor rated ambient temperature also. So, on the nameplate, you typically will have the insulation class, B, F, H, and then you also have a ambient temperature rating. In most cases, 40 degrees Celsius is very common, but if it is, always verify that on the nameplate. And then one last thing on insulation class, keep in mind, you may have a motor with class F rating, but that definitely doesn't mean you're expecting the motor to operate at a temp of 155 degrees Celsius. It's very hot. So most motors will typically run a lot cooler than the insulation class rating, but it does depend on those other factors we talked about, the ambient temperature and running conditions. So the next force we talked about, mentioned in the intro, was voltage. So along with temperature, let's consider the voltage. Verify your rated voltage on the motor nameplate. Sometimes you may have multiple voltages on the motor nameplate. Motors might be dual voltage rated or rated across a range. So you really need to understand what the application is or the incoming voltage is at your plant when you're doing any measurements, like with a multimeter or something. Definitely, we've seen this multiple times, out kind of solving problems in the field. Motors dual voltage rated for 230 and 460 volts. Their customer may be applying 460 volt, and they've got it wired up for 230, and the motor doesn't last very long under those. It actually will run, but it's not going to last very long under those conditions. It's not a safe, definitely not a safe thing. One thing to note, most low voltage motors these days typically rated at 460 volt. There are quite a few 600 volt out there. That was more of a popular thing, in years past with paper mills and other facilities like that. But typically 460 volt is your most common low voltage that you're going to see in your facility. But take into account the grid voltage coming from your utility provider is going to be 480 volt, maybe even a little higher. So that 460 volt rating takes into account voltage drop in those distribution lines coming from the nearest substation or distribution transformer at your site. We've done actually some testing in our lab here that showed a slight increase in supply voltage to a motor, multiple motors across a wide horsepower range actually leads to increased motor efficiency. So at the same time, we reduced the input voltage and to the motor and saw that voltages below that nominal rating are detrimental to motor efficiency. So keep that in mind, when you're maybe later on when we're taking some values for your motor management, we're doing a survey of your facility. There's some other data on this. The Electrical Apparatus Service Association Electrical Engineering Handbook, that's ESA. You'll hear us mention them quite a few, and maybe they're giving some presentations on this as well. But according to their handbook, if you look at a 10% voltage drop, then on the motor input terminals, then the motor design torque would be reduced by approximately 20%. So that's pretty telling on not wanting to under voltage your motors, because you're not going to get the output that you need. So generally, if lower voltage is supplied to a motor, then the motor needs to draw more current to output the necessary torque and speed for whatever application you're connected to. And then the higher current draw leads to heat. And then the overheating will eventually lead to some type of motor failure, whether it be in the windings or the bearings or some component. So continuing on the voltage discussion, voltage imbalance, that's another major problem. And some level of voltage imbalance is very common pretty much anywhere where you have three-phase power. It's very difficult to keep with all the different loads that you may have on each leg of the three phases. It's very difficult to keep that power perfectly balanced. Here in a lab setting, yeah, we can keep it very balanced for our testing. We can also keep it to run testing at 2, 3, 5% unbalance. But in your facilities, it's going to be very common to see some levels of voltage unbalance. So it's good to understand when you know what that voltage unbalance level is, then what does that mean for your equipment? And as I mentioned, we are a member utility organization here at Advanced Energy, so we work with quite a few utilities very often. Typically, the utilities have PPAs, power purchase agreements, in place that sets limits on the amount of voltage imbalance they would provide to a customer, typically in 2 to 3% range. And you may say, well, 2 to 3%, that doesn't sound like much, but 2 to 3% is actually can be very detrimental to the motor population over time. And you see that from some of the graphs here, kind of the derating factors shown in the figure on the left. So the point to be made is that even minor voltage imbalance will lead to horsepower deratings for your motors and your applications. And then keep in mind, we're talking about voltage imbalance because that's really what you can control going into the motor. The voltage, the direct correlation variable to voltage imbalance is current imbalance. And so an industry rule of thumb is that for every 1% voltage imbalance you may see on the motor terminals, then the motor is going to show a 7 to 8% current imbalance. And the high current imbalance, that's going to be very detrimental to your motor operating conditions. As we mentioned earlier, the higher currents on those individual phases are going to lead to extra heating in the motor, maybe hot spots on certain portions of the motor windings. And then anytime you get that heating and those hot spots, we're going to lead to premature motor failure. Voltage imbalance isn't the only thing that causes current imbalance. So another thing that you could check if you use your ammeter, your CNC some unbalanced currents. You want to verify your winding resistance. So, get a simple ohm meter and de-energize the motor, and then measure each of those phase-to-phase winding resistances to verify if you have kind of those some level of unbalance coming from the resistance in the windings that may be leading to that current unbalance. But definitely the voltage unbalance will lead to high current unbalance. Current unbalance is going to lead to some motor failures or premature motor failures. The last force that we mentioned there was friction. So mechanical friction in this case. So mechanical friction for motors is directly dependent on the motor bearings. A good place to start is with your motor alignment. Maybe any parallel or angular misalignment is going to lead to a lot of problems for you, but especially critical to controlling the vibration and mechanical wear. So, keep in mind all your motors must meet manufacturing tolerances when they come from the manufacturer, off the assembly line. And that's if the motor is new, or if it's a repaired motor. Motor repair shops, they're going to have tolerance as well. And some of the key tolerances that those manufacturers or rewind shops are checking for are the rotor balancing, shaft run out, bearing housing, bearing journal fits, and then the shaft passages. And then another key factor with the motor alignment, the correct bearings are being used for the application. For instance, standard ball bearings will be used for like direct coupled loads or lower torque belted loads. But then if you get into the use of higher radial type loads, belted applications, then you want to use roller bearings. So that's something to keep in mind when you're going to purchase. Typically, your manufacturers, distributors, they'll help you in speccing out the motor, but something to keep an eye on if you're going for a rewind or looking to switch a specific motor or match a motor to an application. And then likewise, with horizontal motors, likewise with vertical motors, consider for the application if you have some axial force that's if it's upward or downward or balanced, and then determine from that if you might need a thrust bearing. And then you can also have thrust bearings on the drive end or the non-drive end. And then if you do have a thrust bearing on the drive end, or then you'll likely need a guide bearing on the non-drive end of the motor. And then, one thing to pay attention to, we don't have the slide here, we've had it in the past. The bearings are the number one cause of failure for your motor. So very important to follow your preventative maintenance techniques and routines with the bearings. And what are those? So periodic lubrication and then vibration analysis. So we'll get into those things. We'll get into the vibration analysis a little bit later on. It's a little more complicated. But lubrication, typically your product literature from the bearing manufacturer will give you specific details on lubrication type, how often, how many run hours to be greasing your motors if they have fittings. If you have closed bearings, that's not really an option. But if the motor has open bearings and grease fittings, how often should you be greasing those bearings, and then what is the amount of grease you need to be adding to those bearings? You don't want to over grease the motors. Lubrication type, Polyrex EM is the blue stuff. That's the most common recommended grease that we see these days. When you have specialized applications or specialized bearings, it may be a different type, but that's kind of the most common right now. All right, so quick review. We covered the forces, voltage, temperature, and the overcoming the mechanical friction. Sorry. Let's move on now to what are some of the problems to look for when we're troubleshooting motors. So what equipment and test methods might we use when we are either trying to figure out a problem or also maybe trying to predict almost some problems that may be going on based on some weird sounds or smells or something that you may be hearing in the facility. So first thing to really pay attention to is your motor data. So you need to know the motor data and you need to know the motor history. It's not just, put the motor in place, plug it in, set it and forget it. So when we're talking about motor data, definitely we want to confirm the motor that you have in service is appropriate for that specific application. So how do you do that? Other than what we've already discussed with bearings and some components. So you need to verify the mechanical and electrical characteristics match. So first step, collect some data from the motor's nameplate. If it's a relatively newer machine, you can gather a lot of information from the nameplate. If this is a machine that's been in your facility for 20 years and maybe you've got a dirty process in the facility, you're not going to be able to capture much from the motor, from the nameplate, unfortunately. But if you do have a nameplate, if you can't find it, sometimes it may be on the bottom, it may be on the opposite side of where you can really see well. Try to get a photo or try to take some data off of those nameplates. And then also we mentioned history of the motor. So how long has the motor been in service, or how much runtime has the motor encountered? So when you are troubleshooting motors, if you think the motor failed prematurely, you definitely want to look at in-service time. But another thing to take into account is how long was the motor out of service before it was put into service. So if the motor was a spare, how long was it sitting on the shelf? If it was in your inventory, your spares inventory, was it there for a couple of months? Was it there for a couple of years? Did it come straight from the distributor? If the motor was sitting around for a year without any kind of nothing being done with the motor, then it's going to be more likely to have issues when you put it into an application, especially if it's a critical motor. You're plugging it in and you're running at high run hours or something like that. So many times if you have the motor sitting around for months on end in no controlled environment, no humidity controlled, or maybe you get a lot of rust on the machine. If the motor shaft is never rotated, then items like that lead to some premature failures. So flat spots on the bearing, if you're not rotating your motor shaft, then you might get flat spots on the bearings just from the weight of that rotor sitting down on the bottom side of the bearings, or moisture buildup if you don't have a humidity controlled storage area, moisture buildup on the motor windings. So definitely, it seems like something that may be very straightforward, but it's definitely an important part of the troubleshooting process. So let's take a look at a few steps to take when you're moving forward with eliminating problems occurring with the motors during the storage process. This was a nice tag. Appreciate our friends over at ESA. Again, that's Electrical Apparatus Service Association, for supplying us this. And they set some guidelines on data to take at least monthly on your stored motors. So first, document when the motor was put into storage. So maybe when you bought it, or if this is at your distributor, when did your distributor receive it from the manufacturer? Because the distributors, they'll store motors for you. You don't have to store, them on site unless you specifically want to. So document when the motor was put in storage, and then also document monthly the motor's installation resistance value. You can get a handheld mega ohm meter and just walk around, have somebody walk around, capture the IR values. When you have those IR values with the mega monthly or quarterly, that's going to help trend if you're seeing any type of insulation breakdown. So, we talked about having moisture on the windings, or if there's some contamination in the windings, you're going to see that showing up through breakdown on that insulation resistance measurement. And then lastly on this, you see we're going to document if the shaft was rotated. Again, it seems very straightforward, but you do need to make sure the shaft isn't sitting kind of in the same spot constantly. And when you or whoever's walking around and rotating these shafts monthly, then make sure you rotate the shaft a couple of times completely, and then you line the keyway up with the designated position like on the chart. So that makes sure you're not sitting in the same spot constantly. And it allows for the ball bearing or roller in the bearing race to move, for the grease to rotate completely around the surface. And not only you're not only preventing premature bearing failure with this type of task, but then mitigating any shaft sagging that may occur. And then, as I mentioned earlier, the motor repair shops, the distributors, they do like to offer storage for you if you've got a good relationship or giving them a lot of good business. And also, if you don't have a humidity controlled or a very clean place in your facility, the offsite storage is probably going to be the best option. All right, mechanical inspection be the next step. You've figured out the storage procedures, following proper storage procedures. Let's move into some basic mechanical inspection. So when you perform in any kind of troubleshooting, go ahead and look for the obvious signs first. So it's very simple, straightforward things to pay attention to would be looking for hot spots on the motor frame. So we earlier we talked about hot spots in the windings. If you have a hot spot within the motor windings or inside the motor, that temperature is still escaping to the outer case. Maybe it's cast iron or stainless steel, or not stainless steel, but rolled steel. You have that temperature escaping to the outside, which is likely painted. So you may see from a hot spot, you may see discolored or degrading paint on the outside of the motor. That's not something that you want to just say, oh, well, the motor paint's going away. That's, there's a problem inside the motor that's causing that. So if your motor has, withstood enough heat to show signs of these external hot spots, definitely gives us, a good idea, even without opening the motor, of some of the degradation going on with the components inside the motor, the bearings and windings. Another thing to look for would be the leaking grease or oil or lubricants. So under the motor, around the motor, leaking lubricants definitely play a big role in understanding if the motor bearing grease is getting too hot, or if the motor bearings are not getting enough lubricant. If it's leaking out, then it can't go to where it's not going to where you want it to, or if it's leaking out, it's motor's running too hot. So one other thing to look for, if you see anything on the motor that looks out of place, broken parts, missing parts, missing fan blade, if you have a fan cooled motor, looking at the fan blades, if there's one missing, that's not good. That's going to lead to some accelerated temp rise. If the fan's not there, that's going to definitely, the motor's going to overheat and it's going to fail early or prematurely. Or if you have a fan blade that's missing on, say, a 8 blade fan, and you have 2 of those missing, now when your motor's rotating, the rotor's not going to be balanced anymore. So you're going to have a noticeably high vibration. You might hear that vibration coming through as mechanical noise. And then, also, look at the picture on the screen. Don't forget to look inside the motor terminal box. You see all the rust. This motor appears to have had some water inside of it, a lot of water damage. Look for arcing or water damage also inside the terminal boxes. We are in kind of hurricane season down here in the Southeast. We do have a lot of facilities that may experience weather events and have floods. If you have motors that get flooded out, it's before you start them back up, you need to get all of that moisture or water out of the interior of the motor. And then one other thing to look at, blocked airflow paths on like a totally enclosed fan cooled motor, or applications that you may have that cause the fan cover vents to get blocked from materials in the environment. If you got a sawmill, sawdust particles, rock dust at a crusher or a quarry, concrete, metal slag, all of these things, you've got your motor running there. It's serving some type of pump or rotational process, and then you've got all of this stuff going around in the environment around it. Make sure that your process isn't leading to the blocked fan or blocking air movement coming through your fan. And then some of these things aren't very complicated. You've got somebody who's doing work around the motor, and then they leave a box or cardboard box or some papers out on the job site or out in the plant, and then the motor starts running. It may suck those papers up on the fan shroud, and then now you've got your fan blocked, or a box that's sitting too close to the motor and it's limiting the airflow coming in the motor. So definitely pay attention for that. Keep the areas around your components clean. And then once you've got this visual inspection, taking into account all these aspects we discussed, once that's performed, go ahead and check your rotation by hand. See if you can actually spin the motor shaft. Is it free to rotate? Some applications, you're not going to be able to rotate the motor shaft when it's coupled to the driven machine. So if you can't check for that, go ahead, uncouple the motor, and then check for a free rotation of the motor shaft. When you're spinning it, try to be kind of in a quiet environment if you can. Listen for any noise coming from the rotating parts. A lot of times it's very easy to hear, or even you might feel a bad bearing as you're spinning that, rotating that shaft, or you're going to hear the rotor dragging inside the stator. And then in some cases, if you do suspect a mechanical issue before it becomes a failure, you notice the high vibration coming from the motor, but it may not be clear on where the source of that noise is coming from. And in that case, you want to go forward with a little more complex process and take a look at the vibration spectrum with a vibration analysis. So vibration analysis, that's the most common mechanical test for preventative or predictive maintenance. Here, you buy a spectrum analyzer, and the analyzer will use a fast Fourier transform, FFT, to capture, using an accelerometer to capture kind of the vibration at different frequencies across the range of, across the range of frequencies that the motor is going to be seeing. So usually you will take the accelerometer. It's got a little, handheld piece that's placed on the horizontal and vertical planes of both of your bearings, your drive-in and non-drive-in bearings, and then axially on at least one of the bearing housings. And then when you are doing the vibration analysis, or maybe this is something that you like to, contract out to your distributor or your motor repair shop, there are standards that apply to acceptable vibration limits. Definitely, if you're going around and doing a vibration analysis in your plant, you're going to be doing that with motors that are running. But the limits by NEMA are applied to uncoupled motors. So keep that in mind if you were trying to compare two standardized limits. So like, for instance, the NEMA acceptable limit for resilient mount motors is 0.15 inches per second peak. And then for rigid mount motors, it's slightly less, 0.12 inches per second peak. And again, this is to uncoupled motors. So the limit on the resilient mount motors, that's a little bit higher based on the movement allowed by the isolator, so like rubber or something during the mounting. And normally that resilient mount is seen typically on smaller motors, maybe fans or blower application. So one other thing, if you are taking the readings on motors that are coupled, and then maybe you're planning to take it on, uncouple the motors and take measurements, go ahead and capture your measurements on the coupled motor before, taking it apart from the driven equipment. Because what you may see, if you're seeing a lot higher vibration on the motor when it's connected to the equipment versus when it's decoupled, then your problem, it may be in the alignment, it may be a coupling wear or unbalance coming from your pump or fan or something like that. So once you've taken a look at some of the mechanical components and mechanical inspection, move into your electrical inspection. So where do we want to start? So one thing, it kind of goes without saying, but make sure these tests are performed by someone with experience or someone who's trained in electrical testing. Here you're going to be dealing potentially with live voltage, or you don't want, safety is something to focus on first here. So using a voltmeter, if you're going to check the line voltage at the incoming power supply at the motor, you want to be looking for each line. So if you got a 3-phase machine, each phase or each line to ground, to eliminate the potential for a blown fuse down the line. And then once you've verified that, then you want to check the voltage between those phase to phase, see what the voltage is on the line to line or phase to phase readings. So the applied voltage could be direct wired from like an on-off switch or circuit breaker. It could be coming from somewhere, a little more complex control, like a soft starter or variable frequency drive. When you are performing the test or checking the voltage from the control circuit, like a variable frequency drive, you want to make sure that the power is available at the incoming and outgoing side of the drive in run mode. If it's not, then all right, you trace your problem back to an issue with that variable frequency drive or with that soft starter. Another useful test you could perform when troubleshooting here is if there's an electrical fault in the ground wall and continuity test. So make sure if the motor is powered by a VFD or soft starter, some type of control that has capacitors, that you disconnect the motor leads from them before performing these tests. Because what happens is, you may have some stored charge on the capacitors of those controlled units. You don't want to be feeding any voltage back to those capacitors. It'll cause the capacitors to blow and then destroy that equipment. Continuity test, that's something you can perform with an ohm meter. Test it with the leads coming directly from the start switch or VFD. If you see the continuity, you can eliminate any possible broken power cables, in the conduit or underground. But if the continuity test does fail, disconnect the incoming power cable at the motor, perform the test again between each phase of the motor. And that way you can pinpoint if the failure is in the motor or, if it was in those power cables. If you are still looking for a failure, you haven't determined one at this time by any of the additional other tests, go ahead and try to perform an insulation resistance test. Megger, an IR test is called. That's going to check for any ground faults in the ground wall insulation. And we covered this a little bit previously with the motor storage. And we'll show in the next slide here where that may be beneficial. So this is just a kind of an overall slide. Sorry for all the words on this one, but here we're looking at an example of a 460 volt input AC and 3-phase AC induction motor that won't start. So you're applying power to the motor leads, but you're not getting the start. So once we go through the preliminary tests we covered earlier, testing for supply voltage, eliminate blown fuses, then we move on to the next system component. So the control circuit is tested to make sure the proper supply voltage is coming in and out of the unit. If you're seeing a fault coming from the VFD will show it on its screen, its HMI. or soft starter, then use that code to help troubleshoot, what may be going on. If you suspect a grounded motor, then you can test that by performing the insulation resistance test, which is going to measure, you take the megger and then apply 500 volts DC to the motor, and that's going to measure the resistance of the insulation to ground. The applied DC voltage is why it's important to remove the motor leads from the control circuit. You don't want that feeding back to any soft start or VFD. The recommended minimum insulation resistance at 40 degrees C ambient for most motors, random wound stator coils, is going to be 5 mega ohms. That's if you run the IR test for 60 seconds. So if you're seeing lower readings than that 5 mega ohm value, that may indicate your reduced insulation conditions. So contamination, deterioration from excessive heat, moisture on the windings, some of those things that we discussed earlier. If the motor tests at 0 mega ohms, that's not good. The winding is shorted, and then you got to pull that motor out of operation and go ahead with a repair or replacement. One thing to note here, we use the megger a lot for these activities, but keep in mind the megger can't determine if a complete motor winding circuit is good, as well as determine turn-to-turn or face-to-face faults. So those tests should, you're going to need to get you some more advanced circuit tester if you want to check for that. So that's kind of a the end on the troubleshooting section. We looked at understanding the operating parameters, remove system components until you isolate the problem. And then here are a few of the references, a few that we mentioned, others maybe that we didn't. IEEE 112, that's the test procedure for polyphase induction motors and generators. NEMA MG1, new revision last year, and actually I think that's a free download if you go PDF route. And then also ESA AR100, newly revised a couple of years ago. All of these are going to help you out. Great resources and references when you're stepping through these processes and troubleshooting your motor problems. So let's move into our last section, motor system management. Really by the end of this section, you should have a good idea of where you want to start in your facility if you don't have any kind of motor management system. Or a lot of places do have some type of motor management system in place. If so, then we're going to give you a few tips to help improve your existing program. The good motor management system should make life easier, definitely for you, or if you're the maintenance folks, or if you're not, then make it easier on your maintenance folks. It's going to reduce your costs, reduce your inventory, and reduce energy usage. And then, all of that leads to reduced downtime also. So first off, on this slide, we have a few numbers to kind of get you in the mindset of motor management and why it's important. The average motor consumes at least 50 times its purchase price in electricity usage over its lifetime. That motor purchase price is only accounting for about 2 to 3% of the motor's lifetime cost. A small percentage may be used for maintenance and upkeep, but the overwhelming majority of a motor's lifetime cost, 97 to 98%, is in its electricity usage. Another tidbit, we're estimating about less than a third of end users consider energy costs when you're looking at new motors or making the decision to repair or replace a failed motor. Hopefully by the end of this training, that number is going to go up for those watching. Hopefully everyone that's watching would be considering overall energy costs and lifetime costs for their purchasing decisions. So what are the components, I guess, of a motor management system? We have three: purchasing, O&M, operations and maintenance, and then lastly, making that final decision of repair versus replace for a specific, each motor or specific application. So what are the benefits of a good motor management system, motor management program? Energy savings, cost savings, increased production, shorter downtime, happier management, right? You would have all of those things, maybe less pressure on you, it'd be less pressure on me for sure. Less pressure at your facility. So let's go with an example, kind of a motor management example. So say you're maintenance supervisor at a textile plant. Plant makes yarn. So plant needs to be kept at a certain temperature, a certain humidity to keep the yarn moving on the spinning machines. One way you do this is with an air washer. That keeps the humidity levels where you need to have them. If one of your critical air washers stops working, you got to shut down the process. You follow the methods that we discussed earlier, you troubleshoot what the problem was. Maybe you verify a motor winding resistance issue with your multimeter and an insulation resistance problem with your megger. So you know, for whatever reason, the motor failed. Go back to your motor management program documentation. If you have one, you need one, and know that you have a backup on site for this motor, right? It's a critical application. You got a backup on site. So you disconnect the failed motor, you go pull the spare from your spares inventory, wire it up, align it. Within a few hours, air washer's back up and running, plant process continues, and you minimize downtime even through a full plant shutdown, right? Less pressure, you're still getting the product out to your customers. But let's look at that same situation if you didn't have a motor management program. So, worst case scenario, you're out that day and your air washer stops working. So air washer motor fails. What's the plan for replacement? Are you the only one in the plant who knows what to do in the event of a motor failure, that air washer shutdown? Wouldn't it be valuable to have some documentation that your colleagues, your team could refer to in the event of a motor failure, especially for those critical motors and critical applications? A working motor management system documents changes, maintenance in the motor population, and all of that can be easily be passed to other personnel, other colleagues within the plant. So help save labor hours in the event of a staff turnover. That's a huge thing that we see these days is labor shortage and employee retention. Let's make the job easier on the people that you have there at your facility and be able to solve these problems in a reasonable time frame. So how hard is it to create a motor management system? Not hard. It's just it takes a little bit of time and effort to develop it, and then the upkeep is pretty straightforward. So first step, you need to come up with your guidelines for your three main components. So for purchasing, develop your purchase specifications, normalize which brands you use, list model numbers, consider those life cycle costs as we mentioned, instead of just looking at initial purchase price. Purchase backups for your most critical machines and build up your spares inventory. Maybe that's at your site, maybe that's at your distributor site. If you use similar motors across many applications, you can probably limit the spares you actually need to have on site. And then next step in your policy, operations and maintenance, follow those things that we discussed earlier. Perform the routine maintenance on your motors, preventative maintenance. Focus more of that time on critical motors with high run hours or high usage rates. And then the last part for motor repair, use repair shops you trust. So I'm always going to recommend using some type of third-party accreditation shop or certified repair shop. We'll go into that just a few slides from now. But if you are using the certified shop, they should be able to help you create your repair specifications. And if you bring it up to them and they're not interested, you might consider going to a different shop or looking at a different customer. So next we have an example just to kind of compare the life cycle cost. Looking at the initial cost versus operating costs of a standard electric motor versus kind of a standard medium-sized sedan car, like a Honda Accord, Toyota Camry, Nissan Altima, Chevy Malibu, something like that. Some of the more popular cars on the road. So notice here in the table the purchase price, annual usage, efficiency for the motor or miles per gallon for the car, the fuel cost. It's very difficult with this slide. The fuel costs are changing so fast. This is kind of my best guess of what it may be, right now. Or, but then the last aspect, the lifespan, lifetime. So we use all of those variables to calculate a life cycle cost for each product, and not surprisingly, the average price of the gas is actually different now than it was last week when I put this together. Look at the initial cost of the electric motor versus the car. So cost of the car is about 7 to 8 times that of the electric motor, but the life cycle cost for the motor is about 4 times that of the car. So why is that? And it's all, again, we covered this. It's all in the electricity bills and the electricity usage of the motor. You may be involved in the electricity billing at your facility. Maybe you are, maybe you aren't. If you are, this may not be news to you. But for others, definitely this is eye-opening. When I first saw this, it was really eye-opening for me. $4,000 initial cost, and then $170,000 over its lifetime is really telling. What we'd like to do, kind of finishing up here, last few slides, is dig into the 3 motor management system components just a little bit deeper. So step 1, create your motor purchase policy. Standardize your purchasing, makes it easier to order the products you need and saves you some labor hours. Your purchasing staff needs to be properly trained, so initial cost isn't the only thing you're looking at, or only factor in that equation. Like we just saw from the example, the initial cost actually for a motor has very little impact on life cycle cost. So, one thing you can do is pre-qualify your vendors. Maybe you want to perform testing. Our lab here in Raleigh, they specialize in this. You may want to compare a couple different vendors, or you got a vendor you're using, you're not liking the quality of their products. Doing some testing may give you some good, valuable data to compare, those different products. Third-party validation or testing isn't always necessary, but it can be, very valuable when you're looking to sign a new contract, or, making some of those big dollar decisions for your plant. The next step, motor repair. So motor repair is kind of the third and final part, or final component of the management system. And step 1 with motor repairs is to ensure that vendor, whoever you're using, is providing the quality repairs, high quality repairs. So similar to developing your purchase specification, you need to develop a motor repair policy, or motor repair specification. So here you see a bunch of items listed on the slides you can add to those repair specs. Repair breakpoint. So this may be different for every facility. So one common specification, not saying this will fit for your facility, but a common one would be that you repair all motors over 75 horsepower, but replace anything below. Another specification may be to replace any motor that costs over 50% of the replacement cost. General kind of straight line specifications like that may not work well for your facility if you have motors that are really old, probably very inefficient design. And that's where a breakpoint study can benefit you. Breakpoint study will be tailored to each facility. So we'll take into account not just the repair versus replacement cost, but also the energy savings you would earn with energy efficient upgrades. And then, as I stated earlier, use the accredited repair shops. Can't kind of reiterate that enough. A few of the third-party quality repair programs I'm aware of, ESA accreditation, SKF certified, the Green Motors Initiative, even Advanced Energy has our own program. It's called Proven Efficiency Verification. each of those programs has its own distinctions, own benefits, pros and cons. But just keep in mind the ultimate goal of any accredited repair program is to ensure your motors are being repaired to the highest quality, and that process being used is standardized and followed every single motor, time in, time out. You don't have to worry about it. You have a good process. You're sticking to that process. And then speaking of high quality motor repairs, here's an example kind of showing what may happen when quality control procedures aren't followed. So graph shows two performance curves. This for the same motor, 10 horsepower, 4-pole, 1800 RPM motor. Nameplate full load efficiency is 91%. The orange line on the graph shows the efficiency when the motor was repaired with kind of top of the line, very high quality motor bearings. And then the green line shows the efficiency when the motor was repaired with a lower quality bearing and then also under lubricated. You see there's a huge gap. This is the same machine. It was just repaired in two different ways. Huge gap on the efficiency and performance. So vital to make sure that repair vendor, whoever you're using, is not making mistakes like this, or else you're going to be losing a lot of money in electricity when you put your repaired motors back in the plant. And then we do put in a plug for the motor repair vendors. They are happy to have your business. Typically, they'll keep records for the motors that they've repaired or reconditioned for you. So, when you are updating your management system tracking or looking to add things, they're going to be really helpful for you. Go ahead, keep that open line of communication with your repair shop and your distributor. You don't have to be the expert on staff at your place. You can defer to them. This is what they do for a living. Let them do what they do best. And then kind of the last thing, bringing it all together, creating the policy. Once you have the motor management system in place, keep track of the motor failures and, track your energy costs versus production. Use those numbers to update, improve your facility, improve your policy. This isn't a one-time exercise. This is an ongoing thing. And this is something you want to consistently be improving to maximize the reliability and savings that you're generating through your motor population and upkeep of your population. So summary, when you're purchasing motors, use those life cycle costs instead of just initial cost. Develop and use the purchasing and repair specifications. So you're getting the best motors for your applications and also the highest quality repairs. And then finally, utilize the strategic preventative maintenance techniques that we discussed earlier on to upkeep your motor population and extend the useful life. All right, Kevin, I think maybe I went a few minutes over, but I'll turn it back over to you at this time.
Well, no worry about the time, Michael. I know this is a presentation that's of considerable interest to the plant engineering audience and the other audiences within CFE Media, which includes control engineering and consulting and specifying engineers. We do have a couple of minutes left, and we've compiled kind of a list from other webcasts and VTW sessions, frequently asked questions on this topic. So I wondered if you get a chance to catch your breath and we can maybe run through a couple of these.
Sure.
Question one, is it ever okay to overload a motor?
Yeah, good question. Maybe one thing we didn't discuss here was the service factor. So, motor overload happens often because certain processes, you're going to have variable loads. Motor may be overloaded for very short periods of time, and the rest of the time it's running at 50, 75% load. So take a look at your motor nameplate. Consider that service factor when you're matching it to an application. You don't want the motor to continually run at the service factor load or at overloads, but it can operate there actually comfortably for extended periods as long as you're staying under that insulation class temp rating inside the motor. Because if you are running above that, that's degrading your components. You're going to lead to some premature failures.
Good. Here's a question I hear often on broadcast. How far should a VFD be located from the motor using it?
Yeah, that's a good one. I hear the same question. So as close as possible. That's really the basic answer. If that's not always, that's not always possible, you can't have it right up next to the motor. When you have extended distances between your drive and your motor, maybe you got a control room where you have your drives and then you've got your motors out on the plant floor. Try to use the VFD specialized cables that the VFD manufacturers recommend in their manuals. You're going to pay a little bit more for those cables, but what happens is it's going to limit the peak voltage and rise times being seen. Well, extend the rise time, but limit the peak voltage being seen at your motor terminals. So short answer, try to keep your VFDs as close to the motor as you can.
Good. How many times can a motor be rewound?
Yeah, that's a good question. So kind of a lot of factors at play in answering that or determining how many times a motor could be rewound. I think, specific number of times may depend on how much degradation you see on the insulation in the core, because every time you rewind a motor, you run it up to the burnout temps inside the bake oven, and then you have a little bit of excess core loss. So it's definitely best practice to perform your pre-burn and post-burn core loss test during each rewind, so you can validate or actually see how much core loss you see, and then that allows you to just capture that amount. Once that core loss starts getting too excessive, then you've kind of rewound it too many times. We've seen through our PEV program, proven efficiency verification, we've had clients who've rewound motors 20 times and the motor's still fully operational. Efficiency is still very similar to when it was brand new. So look at each application, defer to your repair shop on that as well.
Good. Can VFDs cause bearing failures on AC motors?
Yeah, not in every case, but definitely they can. I'm not saying they will, but they definitely can. And there are a lot of different things that kind of go into those failures. VFDs, we didn't cover them a ton in this presentation, but they supply kind of a different type of voltage signal to motors than the grid does, and that's called a PWM, pulse width modulated signal. It's kind of like a square wave, more so than a sine wave, what your motor sees from grid power. So a motor controlled by a VFD is seeing, as I mentioned, just in the other question, the motor may be seeing a much higher peak voltages at its terminals than motors that are controlled by your grid fed AC power. If the motor doesn't have, for instance, inverter duty windings, which is very common with a lot of new motors these days, but maybe your older motors don't, and if you don't have a shaft grounding or something like that, some of those devices, then those higher peak voltages end up getting dissipated through the shaft and then into the bearings and lubrication. Degrades the bearings, and then, as we mentioned, bearings are the number one leading cause of failure. So that's kind of how your motor may fail with a VFD.
Good. Final question for today's sensor session, although I'm not sure if this is one question or two. Should vibration sensors be added to all motors or only to motors of a large horsepower? And then finally, does measuring degrade insulation over time?
So definitely best practice to monitor the vibration on any critical applications. So, it maybe if you have large motors, the motors are, higher horsepower, you're going to be using more energy when you run those. But if you have a critical application where, you're on the small horsepower range, 10, 15, 20 horsepower, you still want to be capturing the data on those. So, use that vibration sensor to prevent unexpected or premature motor failures and downtime. And then the second part of that question, does measuring degrade the insulation? So using kind of high potential tests like dielectric tests can actually degrade the insulation over time. That's why we want to use these lower voltages, like with the insulation resistance test. I mentioned, in the material, 500 volts DC is a common. If you're using those low voltages, then you're not going to be degrading the insulation. If you're doing a AC high pot test where you need NEMA prescribes 2 times the rated voltage plus 1,000. If you had a 460 volt motor, that's 1,920 volts. That is, you don't want to be running those a lot, but your 500 volts DC, you're good to run those without worrying too much about degrading the insulation.
All right. Well, thank you so much, Michael, again, for sharing your time and expertise. And we look forward to working with you again in the future. Thanks for your attendance, and we'll see you next time.